For the remainder of the videos in this series, we will be taking a look at simple harmonic motion and waves. Both of these subjects are worth paying careful attention to because they're like a bad penny. They keep churning up over and over and over again in different guises. For instance, when we get to waves, we'll find out that waves actually show up in physics 3 different times in different guises. In simple harmonic motion here, which underpins waves, is itself no different. What's at play here? So remember, if we have, say, a mass attached to a spring, we set the equilibrium position to be x equals 0. Let's say a compressed position here is negative and an extended position is positive. We can write the force of the spring as minus kx, where the minus sign is there to make the direction work correctly. So for instance, if I were to displace my mass over here, it'll be located in a positive x direction, but it would be feeling a force of the spring to the left. So a positive x times negative gives me a negative force, so it's pointing to the left. By the same token, if I were to compress the spring and have my mass to the left of the equilibrium position here, x is negative. And again, what the force is going to try to do is push it back to center. In this case, will be to the right. Well, a negative number times a negative gives me a positive. So this minus sign is there to reflect the fact that this spring force is an example of what physicists call a restoring force. A restoring force is simply any type of force that attempts to return an object back to an equilibrium position. It can be shown that for virtually any restoring force, if your deviations from the equilibrium position are sufficiently small, they all eventually end up looking like this. And so what we're about to do actually has an awful lot of applicability in a lot of different places. All right, so just as a quick reminder of how the energetics of this work, we remember that the potential energy for a spring is 1/2 kx squared. So again, the potential energy will always be positive. And recall here that for reasons of calculus, we set the potential energy to be equal to 0 at x equals 0. So as we go ahead and take a look at our mass on a spring oscillating, let's say it's compressed at the moment, and this is my equilibrium position. If I'm over here at what we call the turning point of the motion, if I were to plot the kinetic versus the potential energy here, we see that out here the energy is all potential. As it starts heading back toward the equilibrium position, let's say at a location like right here as an example, the energy at this point is going to be some sort of split of potential and kinetic. So there's my potential, there's my kinetic, and again, just a quick reminder, the sum of these two is the same as what we had before. Similarly, if we get to the equilibrium position itself, the energy at this point will be entirely kinetic because the stretch is 0. And then here, the force exerted by the spring will be 0, but the object's moving. So it's going to overshoot and will start to slow down. Eventually, it will reach the other turning point. And again, here, the energy will all be potential. So the motion is just going to be to oscillate back. Oops. The motion is just going to be to oscillate back and forth between those two positions. To give a little bit of nomenclature here, we will call this distance here the amplitude. And conventional symbol is a capital A, although sometimes you'll see people use like a capital X. This is the distance from the equilibrium to the turning point, and it's always a positive number. So the position here is x equals plus A. The position here is x equals minus A. Here would be x equals 0, and so forth. So what happens is you move quickly through the equilibrium position, slow down, reach the turning point, go back and speed up, moving quickly through the equilibrium position, slow down, reach the turning point, go back, speed up, and you just repeat this forever and ever. One complete cycle of oscillations, say from here to there, back to here again, that will be called a period. So the time to do that is called the period. And a lot of times, instead of being concerned about the period, we're actually concerned with the frequency, which is 1 over the period. Now, a quick note here. In order to avoid some confusion, we usually write Hz for the unit instead of 1 over seconds. This Hz is read as hertz. It is after the researcher who experimentally demonstrated that light was a transverse electromagnetic wave. And so looking at things oscillating was a lot of what he did. This is done, again, as a deconfuser. Angular velocity, remember, has units of radians per second. And remember, a radian has no dimension. It's just the equivalent of the number 1. And so, much like we write Newton meters for torque and joules for energy to keep them straight, we will write radians per second for angular velocity and hertz for frequency to keep them straight. All right, so our big goal here in this video is going to be to find an expression for the position of our mass as a function of time. And it turns out that this class of problems can only really be solved by guess and check. If you go on and take more advanced math courses, what they actually end up doing is just teaching you very clever ways to guess and check. So we're going to do this by guess and check. And so what does it all have to satisfy? There are 3 big things that we're going to need to satisfy. We're going to need to satisfy Newton's second law. We're going to have to satisfy energy conservation. And we're going to satisfy the definitions of acceleration, velocity, and position. In other words, everything has to be consistent. So Newton's second law, in this case, we can just go ahead and write it down. That's going to, remember, that says the acceleration is equal to F net over m. So this will be minus, I'll write it as k over m times x. So I put in minus kx for the force of the spring. And here I'm keeping track of the minus sign in order to reflect the fact that, again, if we're to the right of equilibrium, the force is to the left. And if we're to the left of equilibrium, the force is to the right. So likewise, for energy conservation, we are going to require that at all times the total mechanical energy, which is the sum of the kinetic plus the potential, so that'll be 1/2 mv squared plus 1/2 kx squared, that's equal to a constant. And then finally, we look back at the definitions of V and A. Should really get rid of that X there. So we remember that acceleration is defined to be the time rate of change of the velocity. So if I were to plot the velocity as a function of time and plot the acceleration, the value of the acceleration at all times should be equal to the slope of the velocity time graph. And the velocity is equal to the time rate of change of the position. So again, if I make plots of the velocity versus time and position versus time, the value of the velocity graph should at all times be equal to the slope of the position graph. So with all of that in place, I'm going to go ahead and make a guess. And I'm feeling incredibly lucky with this guess, but it is a guess and we'll have to check it. I'm going to guess that the position as a function of time will be equal to the amplitude times the cosine of 2 pi ft, where f, remember, is the frequency. That'll be equal to 1 over the period of oscillation. So let's see if there's, let's see if there's some way that we can figure out the acceleration and the velocity. This seems like a natural way to do things. If we can, given this expression for position, if we could figure out some way to come up with the corresponding velocity and acceleration functions, then we can go ahead and stick those into energy conservation and Newton's second law and see if we can get them all to work. And if we can, then our job is done here. Well, it turns out that there is a way we can do that. So what I'm imagining here is I'm imagining that there's a wall. And if we just imagine that we have, like, say, a rubber stopper or something like that at the end of a string going around in a circle like so. And then way over here somewhere, we've got a nice uniform light source. So it's shining light very uniformly on the ball. Let's say, for purposes of discussion here, we'll make the radius equal to the amplitude of my motion, for reasons that'll become apparent in a second here. So let's say that our, actually let's make it even a little more blatant. There we go. Let's say that we are out here moving around at some angular velocity omega. And we are, and at time 0, we passed through angle 0. If that's the case, then this angle will be equal to omega t. And what we're interested in is the x-coordinate of the shadow that's being the shadow that's being cast on the wall. This shadow would be the x-coordinate of this. If you actually try setting something like this up, you need a pretty strong light, and be careful not to break anything. You'll look at the shadow of the stopper as it's moving back and forth, and it'll look an awful lot like a mass attached to the end of the spring. They'll both have the same kind of boingy, boingy, boingy thing going on. And that should make you feel pretty good. Well, we can figure out what the x-coordinate of my shadow is. So this would be x equals 0 right here. It's my x-coordinate as a function of time will be equal to this radius, a, times the cosine of this angle here, which is omega t. All right, well, we're almost kind of there. So this goes around 2 pi in one period. So if we make this if we make the period of the stopper moving around the same as the period of our mass on the spring, then we would be requiring that omega be equal to 2 pi over the period. And remembering that the period is 1 over the frequency, we can write that as 2 pi f. So substituting all that in, we get that the position would be equal to the amplitude times the cosine of 2 pi ft. Well, we're feeling pretty good there. We at least got our, covered our guess here. So it's the x-coordinate of this stopper moving around in a circle. Alrighty. So what's that going to get us here? Well, the idea is that if we go back to looking at uniform circular motion, we remember how the velocity and the acceleration are related. So let me just copy and paste this here. So we can find the velocity. So the next step here is we're going to find the velocity of my ball and take the x-coordinate of it. There, not too bad. Good. Alrighty. So let's go and take a look here. So we know that the velocity of the ball is going to be directed tangent to the circle. So this is v tangential here. And similarly for our shadow, this would be the velocity of my shadow here. But the velocity of my shadow here is the same as the x-coordinate of v tangential. So the idea here is if we can figure out what angle is theta in this triangle here, we can then go ahead and take a component. So let's go and do that. By alternate interior angles, this angle here is this angle here. Now, this angle here and this angle here, if I look at this to here, v tangential always makes a 90-degree angle with respect to the radius. So this angle will be the complement of that angle there. But there are 180 degrees in a triangle, and this is a right triangle here. So this angle is the complement of this angle here. Well, the complement of the complement is the angle. So this angle right here is this angle, is that angle, theta. All right. So then I can go and look at this and say, all right, then Vx here is going to be the opposite. V tangential is the hypotenuse, so I'm going to need a sign. So the velocity, and I'm leaving a space here. It's going to be V tangential sine omega t. And then I need to put in a minus sign here because you can see here it's pointing to the left. And if you follow this through all quadrants, you'll realize that you need a minus sign everywhere along to get this to work out. So we remember that V tangential, V tangential is, there we go, small t. V tangential, remember, is equal to the radius times the angular velocity, so I'll write omega a. And again, here, we remember that omega is 2 pi f. So this will be 2 pi f times a. And again, here we'll remember that my omega is equal to 2 pi f there as well. So making all the substitutions, we get that the velocity of my shadow here, which, if my guess is correct about the motion of the mass at the end of a spring, if my guess is correct, its velocity would have to be minus 2 pi f a sine of, oops, let me move this, sine of 2 pi f. Oops, just 2 pi f t. There we go. So what we got so far, so this is my guess, and I observed that my guess is the x-coordinate of this ball going around in a circle. So I then worked out what the x component of the velocity of the ball going around the circle is, to get that this would have to be the velocity of the mass at the end of the spring, if my guess is correct. All right, so we need to do this one more time. Oh, oops, before we run away with that, we can also observe what the maximum speed is going to be. The maximum speed, remember the sign of anything is going to always return a number between -1 and 1. So I get my biggest value here, since I got minus sign in front. If that's -1, it'll be that. So the fastest my mass at the end of spring could ever go would be equal to 2 pi f a. Alrighty, so let's go and, whoops, do this again, this time to get the acceleration. So this might even be a moment where you might want to try to pause the video and try to find an expression for the acceleration yourself, doing what we've done before. So if you go ahead, if you want to try that, go ahead, pause the video, and then get back with me. All right. Since my mass is going around in uniform circular motion, here its acceleration will be pointing straight into the center of the circle, and it would be a centripetal acceleration. Again, the game is going to be the same. The ball we know is, the mass is accelerating towards the equilibrium position. So its acceleration would look like that. That would be this piece right here, a sub x. So again, the same game, we have to play the same game as before. We have to figure out what angle is our angle theta. In this case, it's this angle right here by alternate interior angles. So again, same deal here. We can write the acceleration of the shadow here, which is the x component of the acceleration of the ball, will be equal to minus a sub c. And again, the minus sign is just because we're pointing to the left. And again, you can try this in all 4 quadrants, and you'll see that you always need the minus sign. Cosine of omega t. we remember that the centripetal acceleration of anything is the radius, which in this case is a, times omega squared. And omega, remember, is 2 pi f. Okay. So we can, and similarly here, that omega will also be 2 pi f. So if we make all the substitutions here, we'll get that the acceleration as a function of time will be equal to minus 2 pi f squared a cosine of 2 pi ft. And similarly, we can figure out what the maximum value of the acceleration can be. Again, here it would be when a cosine's -1 to make that negative go away. So the maximum value of the acceleration will be 2 pi f squared a. Alrighty. So we haven't... So what we've done so far is we guessed that the position goes as the amplitude times cosine of 2 pi ft. And so now what we've been able to do is, by recognizing that this is the x component of the motion of something going around in a circle, we used our results from uniform circular motion to get what the expressions for the velocity as a function of time and the acceleration function of time would have to be in order to satisfy the definitions of velocity and acceleration. So we've already done that part. So now what's left in our guess and check action is to see, so let's just go ahead and take a look at what we've done so far. So the definitions of V and A are consistent. We can go ahead and check that one off because we constructed it that way. All right. So now let's go and take a look at Newton's second law of motion. Are we consistent with Newton's second law of motion? All right, so remember that required, we said A is equal to F net over M, and we observed that that would be equal to minus K over M times X. Now this has to work at all times. So we're just going to go ahead and substitute in the expressions we got for A and X and just see where that takes us. So the acceleration is a function of time, remember, we said it was 2 pi f squared A, whoops, with a minus sign in front, that's important, cosine of 2 pi ft. Here I have a minus a K over M, and then X, remember, was A cosine 2 pi ft. Well, let's just see what all we can cancel away. We can make all the minus signs both pluses. We can cancel the cosines. We can cancel the A's. And we're almost there. We do have, in order for us to be able to be consistent with Newton's second law, we've found a constraint on what the frequency has to be. So we can say that, yes, this is satisfied, but it requires, if we go ahead and solve for the frequency here, 2 pi f squared equals K over M. Take the square root, 2 pi f equals root K over M. Oh, yeah, there it is. We can satisfy Newton's second law as long as the frequency is given by 2 pi f equals root k over m, or if you prefer, you can write f equals 1 over 2 pi root k over m, whatever makes you happier. So as long as that's true, then we've satisfied Newton's second law. Okay. So the last thing we have is it consistent with energy conservation? So this one's going to be a bit of a slug, but let's work through it. So remember, the total mechanical energy is equal to the kinetic plus the potential. So, and we want this to be equal to a constant. So let's see if it is. So the kinetic energy is 1/2 mv squared. The potential energy is 1/2 kx squared. So we will go ahead and put in our expressions for v and t into each of these. So we'll have 1/2 m, and our expression for v, remember, was that it was equal to minus 2 pi f a sine of 2 pi f t squared. And I'll add to that 1/2 k, and we'll substitute in our expression for x. That's just going to be a cosine 2 pi ft squared. Whoops. There. All right, let's expand the squareds through everything. That might help us a little bit, maybe. So 1/2 m. Squaring a negative just gives me a positive, so the sign goes away. I'll have 2 pi f squared, a squared, sine squared of 2 pi ft. Remember, sine squared means you take sine of 2 pi ft and then you square the thing. That's just the notation mathematicians use. It's not some funky function called sine squared or something like that. So plus 1/2 k, squaring this out is going to give me an a squared cosine squared of 2 pi ft. And it looks for a hot minute like maybe all is lost, but then we remember that 2 pi f we said was equal to root k over m, or 2 pi f squared would be equal to k over m. So we're going to make that substitution right there. So this will give me total mechanical energy is 1/2 m, and then we'll put in for 2 pi f squared this k over m, a squared sine squared of 2 pi ft plus 1/2 k a squared cosine squared 2 pi ft. Alrighty. Hey, the m's cancel. And now each term has a 1/2 k a squared. Let's pull that out and see where that takes us. Maybe it's somewhere good. So we'll have 1/2 k a squared times sine squared of 2 pi ft plus cosine squared of 2 pi ft. And I sit back and it's like, man, that seems like a really familiar trig identity. And so sure enough, I go and consult my table of trig identities, and I find that the sine squared of some angle plus the cosine squared of that same angle is always equal to 1, regardless of what the angle is. So the whole thing in brackets is just the number 1. And we get that at all times, the total mechanical energy is 1/2 Ka squared, which is the potential energy when we're at the turning point. But we've shown that it is that at all times. So we can go ahead and check off that, yes, indeed, it is consistent with energy conservation. All right, so that's quite a bit right there. At least there was good, useful review of uniform circular motion and energy conservation, so that was good from that perspective. But let's just recap where we went with this. So we observed that the force was minus kx, and we worked out that that meant that you'll be going fastest through the equilibrium, slow down when you get to the turning point, turn around, come back, speed up, slow down, turn around, come back, boingy, 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 forever. Similarly, the energy will switch back and forth between all kinetic in the middle, all potential at the ends, and a mix somewhere in between. To get the expression for the position as a function of time, it turns out the only way you can do it is by guess and check. So we required that we be consistent with the definitions of A and V and Newton's second law and energy conservation. We made this guess right here, which turned out to be a very fortuitous and correct guess. And we went ahead and observed that that was the same difference as the x component of a ball going around in a circle. Since we knew how to get the velocity as a function of time, the velocity of a ball going around a circle, we could get the x component of that to get the velocity of my mass on the spring. And same thing with the acceleration. So the definitions of velocity and acceleration were satisfied by construction. We plugged that into Newton's second law and found that everything works as long as the frequency of oscillation is 1/2 pi root k over m, where k is the spring constant and m is the mass. And then finally, we checked our work off against energy conservation. It was tedious, but at the end of the day, with the help of the identity sine squared plus cosine squared equals 1, we saw that the energy is indeed a constant and equal to the potential energy at maximum stretch. So we'll finish this out by just looking at the intuitive picture I had alluded to earlier. I said if we plot the position, velocity, and acceleration as functions of time, we should find that at all times the velocity is equal to the slope of the position, and that at all times the acceleration is equal to the slope of the velocity. So I'm just going to make plots of x, v, and t as functions of time. And I'm going to mark out quarter periods here. And I'm already going to beg your indulgence for what will be my almost utter inability to draw a half-decent sine wave. So we're going to look at one entire period of oscillation. So each of these hash marks is a quarter of a period. Right there. So let's go ahead, and here I will mark this is A, that will be minus A, Similarly, that will be 2 pi FA and minus 2 pi FA. Then finally, this will be 2 pi F squared A and minus 2 pi F squared A. All right, let's do the position in red. That sounds as good as anything. So remember, that was a cosine. So it's going to start at a maximum value at time 0. Hit the other extreme at half a period. Go through the equilibrium at 3/4 of a period. And I tried. And max out, there we go, at 1 period again. Let's draw just a little bit more of it. And similarly, if I were to draw my velocity as a function of time, I guess let's use green for that. Remember, that was minus the sine. So the sine is 0, and it would normally be 1 at 1/4 of a period. But because of the negative in front, they'll make it minus 0, positive 0. We'll do just a little past it. And what's good for acceleration? I guess purple. That's negative cosine. So I don't know, something like that maybe. All right. So while it's certainly, if I were a much better artist than I am, you would be able to lay a ruler against any of these graphs, measure the slope, and check it against the corresponding values. But we can at least intuitively check it at each of the quarter periods. So if we look at time 0, here the slope is 0. Slope 0 means the value here is going to be 0. Here, if I look at this, I'm going through an inflection point. And an inflection point, that means the slope is a max. And it's a max negative. And that's a max negative right there. Similarly here, the slope is 0. The value is 0. Again, here, I'm going through an inflection point. So that's a maximum slope. Here it's a maximum positive slope, and the value here is positive. And slope 0 here, value 0 there. And then we can repeat this here. So this is an inflection point, maximum negative slope, maximum negative value. Slope 0, value 0. Inflection point here, so I'm at maximum positive slope, maximum positive value. Slope 0, value 0. Inflection point again, maximum negative slope, maximum negative value. So for at least those points it checks out. And if you want to draw it more carefully and use a ruler, you could check any other point that you want in between, and you'll be able to convince yourself that it works. All right, so in the next series of videos, one of the things that we will be tackling is actually applying this to all sorts of different oscillatory situations. So catch you on the flip side there.